Section 6, we have a couple of boys cooking in the background, so if you hear any weird sounds, that's the mystery sound. And just hope it's not too distracting. Alright, so I need to share the space with them. So, alright, so what are we talking about here in Chapter 6? Wait, the pressure doesn't depend on the identity of the gas? Are you serious? Do you mean to tell me that PV is equal to nRT, right? That has nothing to do with the gas. Like there's no, we never say, well, the pressure of helium, right? It's simply the pressure and the volume, the moles, R and T. These are all independent of the identity, right? Have nothing to do with the identity of the gas. This is what section 6 is about. So if that's true, this is a figure from I think section 2, maybe section 3. If that's true, then the pressure in this jar is the same if that's X, and this is an X particle, and this is an X particle, and that's a Y particle, and that's a Y particle, and that's a Y particle, and there's an X, and there's a Y, and there's an X, and there's a Y. It's all the same. It doesn't matter if these are all X's or if these are all Y's, right? Or another way to say that, it doesn't matter if it's a mixture of helium and carbon dioxide, right? Or helium and neon. Doesn't matter. So over here, I might say, all right, well, I've got some carbon dioxide. Can you see that color? Let's change colors here. This is a section that's going to be very simple to you if you get it, right? So here's a carbon dioxide molecule. Here's a carbon dioxide molecule. Here's a helium molecule. Here's a helium molecule. Here's a xenon molecule. Here's a carbon dioxide molecule. And here's what else, right? Neon, xenon, right? It doesn't matter what these are. It turns out that PV is equal to nRT, where the pressure is the pressure inside there, the volume is the volume of the jar, and the N is, watch this, we've been carefully saying this, moles of gas. So in this case, it would be moles of CO2 plus moles of xenon plus moles of what? Neon and whatever else other gases I had in here, right? That would be the moles. Amazing. Okay, what does that mean? Let's look at this now. Now we'll talk about, we'll say that if we have some container, I'm going to draw that jar again. Okay, let's go back to red particles, red ink. Okay, suppose we've got some X, and some X, and some X, and some Y, and some Y, and some Y, okay? Now, if that's true, we've got a pressure, PV is equal to nRT, right? Well, this is moles of everything. That's moles of gas, all right? And this is the pressure of everything, okay? Well, what we could say now is that we might have a partial pressure of X, right? See my three X's? And a partial pressure of Y. I might have should have chosen A and B here, right? Tro uses A and B in the argument. I think it's a good idea to do that. I use X and Y, and then we're going to use X for something else, okay? That's not really an X, it's a chi. But anyway, all right, let's suppose we've got X, X, and Y. So we have a partial pressure of X, and the partial pressure of X is equal to the volume times the moles of X, RT, right? And the partial pressure of Y is equal to the volume times the moles of Y times RT, right? Just exactly what you would expect. Okay, now it turns out that X is occupying this whole volume. Let's say that the volume here of this jar is 1 liter. Okay? If the volume is 1 liter, can you see that X is occupying the whole space just like Y is? Alright, so these volumes are not additive, but the pressures are additive. What adds up? The pressures add up, okay? But not the volumes, because they're both occupying the same volume. And the temperatures don't add up all either. But the moles do. The moles and the pressures add up. All right? So the total pressure then is going to equal the partial pressure of A plus the partial pressure of B. All right, and the mole fraction is something we're going to figure out. How much of this pressure is due to A? Well, it turns out, can you see that I've only got 7 particles in here? Let's say that every particle represents a mole. The mole of X, if every particle represents 1 mole, what are the moles of X here? And what are the moles of Y? And what are the moles total? Okay, let me say that again. It's really important that you try to answer this, all right? Because it's so that you're not sort of just getting swept along. Each particle, wow, represents a mole, all right? All right, thank you, Pleasure. As I'm doing this, a boy comes and hands me a dinner. Thank you so much for that dinner. Each particle represents a mole. So if that's true, what is the moles of X here? Can you see it? It's 3 moles. What's the moles of Y? 4 moles. Thank you so much. Thank you. 4 moles of Y. And what's the moles total? It's 7 moles total if each particle represents a mole in here, okay? Do you see it? All right. So if that's true, we know that R is equal to 0.08206 liter atmospheres per mole Kelvin. Temperature, I haven't told you the temperature yet. Let's say it's room temperature, which is about 298 kelvins. Okay? Can you see we can figure out what partial pressure of, we can figure the partial pressure of X and the partial pressure of Y, and we could add them together and get the total partial pressure. It's going to fit very nicely when you do an example. Okay, and the one last term I want to define here is mole fraction. Mole fraction. It's going to totally make sense. The mole fraction, which is really a chi, of in this scenario up here, X is equal to the moles of X over the moles total. And what is the mole fraction of X in this scenario here? I'm going to do chi, okay? I should have made that a chi. A chi of X is equal to, can you see it? It's 3/7. 3/7. And I can't do that in my head. What is 3/7? It's about 0.4, oh, I don't know, 0.44? 0.4 something. I can't do that. Can somebody tell me what 3/7 is? 3/7. Somebody tell me what 3/7.
0.428.
0.428. Thank you.
571.
0.428571. Okay. So, obviously to 1 sig fig, it's 0.4. Okay? And that's what we're doing here, is 3/7. But these are actually exact numbers, aren't they? So we would have to say, I don't know. Let's say 3 sig figs, 0.429. All right, so that's the mole fraction of X, right? What's the mole fraction of Y? The mole fraction of Y is going to be 4/7. 4/7, which is going to be 0.5. 0.57, oh, I don't know, 0.57 something, right? They're gonna add up to be 1, of course, right? Because 1 is the whole. All right, so let's do an example. 1 liter mixture of helium, neon, and argon. I'm gonna make some notes here. Oh, yeah, argon, helium, and neon are all in this jar here, okay? Has a total pressure, All right, I'm going to go across here. Helium, neon, and argon has a total pressure of 662 millimeters of mercury. I'm going to take everything to atmospheres just in case I need that, okay? So 662 millimeters of mercury (760 millimeters of mercury over 1 atmosphere) And 662 divided by 760 is 662 divided by 760 is, just a second, I'm going to see if I can get some response from 662. Alright, I'm going to get my own calculator.
62 is what?
662 divided by 760?
Sorry.
Yeah, it's my fault. I should have.
0.8710526.
0.871 526?
0.8710.
526?
Yes, sir.
Okay, thank you very much. Alright, so that's the total pressure in atmospheres. If the partial pressure of helium, I'm sorry, Dave, I'm going to need another one, okay? 341 over 760?
0.44868.
0.44868. And that of, and what's 112 over 760?
0.14736.
Thank you so much. Neon is 112. 14736. What mass of, oh, what mass? Okay, so we got partial pressures here. Now we're going to come up with the partial pressure of argon. But they're asking about mass. So yeah, it's a good thing we did this. All right, so P, I got the P's for all those. V, N, R, T, great habit. Wow, what a genius. 0.08206 for all of them, all the way across. That was a little bit of sarcasm. It just didn't sound very nice, though, did it? And 298K is the same for all of them. 298K all the way across. And the moles is not additive, but this is 1 liter. 1 liter all the way across, right? I mean, I'm sorry, the moles is additive. So what I'm going to do is I'm going to first of all find the partial pressure of argon. And then I'll start thinking about this. All right, so the partial pressure of argon is going to be this much, the total, minus these two, right? So I shouldn't have, it's going to be easier. Yeah, let's do this. 0.8710526 minus, Dave, would you do one more for me, please?
Yes, sir.
Would you add 0.44868? 0.44868 to 0.14736? And then subtract that, so just make that a minus on it now. Then subtract that from 0.8710526, 0.8710526. Thank you. Give me one more digit.
0.
Thank you. Let's see if we believe him. That's about 0.9. This is about 0.45. This is about 0.15. Yeah, that's perfect, right? So this makes sense. I'm going to show this in red. This is about 0.9. This is about 0.45. This is about 0.15, right? 0.9 minus 0.6 is 0.3, and that's about 0.3. Yeah, good. Thank you, David. So we have the partial pressure of argon in atmospheres. We have the volume of atmosphere. We have everything except that, right? And we go from moles to mass very easily. Aha. E-Z. Okay. So we're looking for moles now. And moles is equal to PV over RT. We've done this a bunch of times. P 0.2750, and it's in atmospheres already. That was smart to do that in advance. V is 1 liter. It's really 1.00, okay? So this is 3 sig figs. We have this to a bunch of sig figs. I'm going to say 5. It's more than that, but it's really 3 sig figs. 0.08206. And then the temperature is 298. Is that right? Yep. Okay, so the moles then is going to be, poor guy, I probably should do my own. I'm going to do my own now. I'll leave that guy alone. the moles is going to be 0.2750 times 1 divided by 0.08206. Crud, I got that wrong. 0.2750 times 1 divided by 0.08206. Man, my thumbs are not working right. I got to start over again. 0.2750 times 1 divided by 0.08206 divided by 298 equals 0.00125. 0.00125. And this is moles of argon, right? And if I want to go from moles of argon to grams of argon, I have to define, I've got to multiply, because the moles have got to cross off, right, by the formula weight of argon. And the formula weight of argon is 39.95. Inside cover of your text is 39.95, and this is 0.00112, no, 11, 2, this is a 1, 2, 4, 6, okay, times 39.95 equals 0.449. Okay, 0. I don't have room here now for my mass, but this was 0.0012, or rather 112456, I think, right? And then we convert that to mass, and the mass then goes to 0.4493 grams, because I had grams here, right? That was grams of argon. That was grams of argon. Looks like it's going to be in 3 sig figs. There's 3 here, 3 here, 3 everywhere. 3 sig figs. 0.449 grams of argon. And that's our answer. 0.449 grams of argon. All right. Did I get the question right? We've got more questions to do here for this section, don't we? All right, let's do another question. Okay, I'll try to go a little faster this time. A 12.5 liter scuba diving tank. All right, so immediately, it's helium and oxygen. Okay, so helium, oxygen, PV. I'm not sure if I'm going to need this. Total nRT. And that's all the way across, right? The temperature is 298. All the way across. I'm not putting the units in to save myself some grief, but remember, please, I'm religiously putting this in kelvins, because this is in liter atmospheres per mole Kelvin. That'll be in moles, this will be in liters, and that'll be in atmospheres, religiously, to keep things simple. Containing that many grams. Oh no, I don't have moles of this, I've got grams. It's okay. I'm like a genius between going back and forth between grams to moles, right? Easy. So let's do that. 24.2 grams. I'm going to leave the units off, keep everything in grams and grams per mole. And oxygen is 4.32. 4.32. Can you see this is in this column here? Okay, grams. And the formula weight of helium is 4.003. And that of oxygen, 16.00. Okay? And so grams divided by grams per mole. So this is going to be grams divided by grams per mole is going to give me my moles. 24.2 divided by 4.003 is equal to 6.0455. 6.0455 and 4.32 divided by 16 is equal to 0.27. Is that possible? 0.270. Yeah, look at this. Yeah, it is, because these are both 4 and 32 are sort of multiples of 16 or factors of 16 or something like that. That makes sense. And even 0.27. And also, there's a lot less oxygen than helium, and it's a lot bigger. So yeah, that makes sense. Okay. And the volume is 12.5 liters for both of them, right? 12.5 liters. So let's find the partial pressure of helium and the partial pressure of oxygen. So P is equal to nRT over V, which is equal to, in the first case, N is, well, let's do 0.27 first, if you don't mind. It's still in my calculator. 0.27 0.27 times 0.08206 times 298 divided by 12.5. Crud. I got this, my thumb, it's just not going right. 0.27, gotta start over again, times 0.0, no, clear. 0.27 times 0.08206 times 298 divided by 12.5 equals 0.528. 0.528. And I don't really have a good sense if that number makes sense or not, right? I can see 300 times 0.08. I don't know. That's about, about 1. Sure. Okay. I'm going to say that makes sense. That's the partial pressure. That's in atmospheres of this guy here. 0.528. Now this one needs to be bigger, right? Because I got more moles in it. So let's check our math here. 6.0455. Man, 6.0455 times 0.08206 times 298 divided by 12.5 equals 11.827. Yeah, that makes sense. 11.827. Can you see this is like, so that's almost double of that. That's almost double of that, a little less than double. All right. Calculate the mole fraction and partial pressure of each component. Aha, okay. So I've already got my partial pressures of each component. And then the total pressure is just going to be the sum of those two, of course, right? All right, so the total pressure is going to be 11.827 plus 0.528 equals 12.355. Well, let's do sig figs now. With 3 sig figs and everything, that's going to be 12.4. 12.4 atmospheres. Pretty high pressure, right? Pressurized. Okay, now the mole fraction then, of course, the mole fraction of helium is going to equal the mole of helium over the moles of helium plus the moles of the other guy, right? Oxygen, which is equal to 6.0455 divided by 6.0455 plus 0.27. Okay? Careful now. That's where people are going to get that one wrong. They're going to add 0.27 at the end. 6.0455 divided by, well, you know what? 6.0455. 6.0455 plus 0.0, crud, man. 6.455 plus 0.27. That's on the bottom. It's 6.3155. So it's 0.957 is the mole fraction. 0.957. And we can do the same thing for the mole fraction of oxygen, but it'd be easier, I think, just to say that 1 minus 0.957, which is equal to. Can you see why we would do that? Zero point 0428. Okay. All right. Now this is an exact number, right? 1 because it's 100%. So how many? Let's just use 3 sig figs for both of those. Frankly, I don't have the patience right now for finding out. There's the mole fraction of helium. Here's the mole fraction of oxygen. Here's the partial pressure of oxygen. Here's the partial pressure of helium and a total pressure. And everything's labeled so nicely, I'm not going to worry about doing anything else. Okay, so hopefully that was faster. I think we have another example here. Oh, yeah. Collecting gas over water. All right. Okay, so here's the challenge with this. It's really not so bad as it looks, but it's, this is a classic reaction. I think every chemistry textbook is going to describe this reaction here, where you take a zinc metal and you put it in a bath of HCl, a solution of HCl, and it's going to make H2 gas. That's what this is, okay? So these little bubbles here, these things are H2. I mean, it's labeled over here, okay? So this is hydrogen gas that's coming out. Well, we might want to say, if you wanted to find out very precisely how much hydrogen gas is being formed, then one way you can do that is you can evacuate this tube and then have all the gas that come out here get collected here, and that can collect the volume very nicely. Okay. Here's the problem. If you're doing it over water, you're going to have some water molecules in there too, because you have some water vapor. And there's your water vapor. Do you see it? Okay. So what we have here is really the same thing we had before. It's a mixture. The pressure total is going to be the pressure of H2 plus the vapor pressure of water, right? Because you've got different gaseous particles in there. It's really just what we had before, where I was using, X and Y. Now we're going to use H2 and H2O. Okay, so collecting over water is not nearly as bad as it looks. It's just you're going to have a mixture, except in a lot of weird words, right? Collecting a gas over water. You're like, what the heck is that? Well, this is what it is. The apparatus looks like this, and you've got your gases going in there, but hydrogen is not the only thing in there. If hydrogen were the only thing in there, then this would be 0, right? And the total pressure would be the pressure of hydrogen. But actually, there's water vapor in too. So let's do a problem like that. In order to do it, we need to know the vapor pressure of water. Like how much water is in there, right? Well, the vapor pressure of water at 0 is pretty small. Like at 0 degrees Celsius, there's very little water vapor in the air. At 25 degrees Celsius, which is sort of where we live, there's that much water in the air. That's the partial pressure of water, and it's called the vapor pressure, okay? But there's water in the air that you're breathing right now, right? It's called water vapor, and they talk about the humidity of water on any particular day, like a really humid day. Well, this is the vapor pressure, given, I don't know, given different temperatures and different temperatures and different factors that go into that, okay? So 23.78 is the vapor pressure of water, and that's what that's about. That was a lousy explanation, I know it. If you're a chemist and you're listening to my video, just bear with me, please. But I really want to emphasize that we're looking for partial pressures, and we need this table. Okay, so collecting gas over water. In order to determine the rate of photosynthesis, the conversion by plants of carbon dioxide and water, blankety. Oh, man. All right, what a mess. Now, the oxygen gas emitted by an aquatic plant, all right, over water at a temperature. All right, so we can see it's gases over water, and we see that one of the gases is oxygen. So I'm just going to say oxygen. Are you okay if I just do OX? I mean, that's obviously not the symbol for oxygen, but I don't want it to look like a 0, okay? So PVNRT. Total. The oxygen gas emitted by an aquatic plant is collected over water. There's my other gas. At a temperature of 293 K. And a total pressure of 755.2 millimeters of mercury. All right, so since I'm using 0.08206, I really need to convert this millimeters of mercury to atmosphere. 755.2. Right? I know we've done this a bunch of times, but I want to write it out each time just to. All right, so it's 755.2 divided by 760. $755.2 divided by 760. 0.99368. Okay, aha, total pressure. 0.99368 atmospheres, right? I'm going to go to red now that we've got everything written down, okay? Oh, so over a specific time period, let's go one more thing here. In black, 1.02 liters, 1.02 liters. Oops, 1.02. This is 1.02, right? And remember, the gases occupy the same space, so those are not additive. What mass of oxygen is formed? Okay, so we need to find this, and then we're going to go to mass via formula weight, right? So the pressure, okay. Well, here's what we know. We know that total pressure is equal to the mole fraction times the partial pressure of, the mole fraction of, well, A, the partial pressure of A is equal to the mole fraction of A times the total pressure, right? So once we find the mole fraction, right? Okay, so what we've got to do, sorry folks, look, I said oxygen and I put it in water. It's really over here, okay? It's not that, that's water. All right, getting a little bit rushed here. All right, so let's slow down a little bit and say, let's calculate what we know we can calculate. Suppose we have no idea what to do here. You don't know the partial pressure and you don't know the moles, but we do know the total pressure and the total moles because we have all those things, right? Another thing that we know is we know the vapor pressure of water at 293, right? So I'm going to look at this. I don't want to take the slide back because it's 293 is really 20 degrees Celsius, right? So what's the vapor pressure? Please look this up in your book. It's on page 197. You need to do this. Page 197, what's the vapor pressure of water at 293 kelvins? It's 20 degrees Celsius, right? So it looks like it's 17.55 millimeters of mercury. Crud, man. All right, I gotta convert this into atmospheres. Divided by 760 is equal to 17.55 divided by 760 is equal to 0.02309. 0.02309. And that's going to tell us the partial pressure of oxygen now, right? Because we know that this plus this in pressures is equal to that. Okay? Plus 0.99368 equals 0.97059, right? And can you see that I now know this, right? N is equal to PV over RT, which is equal to 0.97059 times V, which is 1.02, divided by 0.08206, divided by 293. Okay? Times 1.02 divided by 0.08206 divided by 293 equals 0.041175, and this is moles of oxygen gas, right? It's oxygen gas, so it's O2. Grams per mole of oxygen gas, 32 grams per 1 mole is equal to, divided by 32, is equal to 1.29 times 10 to the negative 3 grams of O2. Wow. All right, sort of a clumsy solution. Surely it's correct. Let me look here at my notes before I move on. I'm not prepared, I think, to ask if it makes sense. Yeah. Okay. All right. Looks like the book's got a slightly different number, invariably due to a rounding error. I'm going to move on. I think that's it for this. That's it for this section. I gotta get a cup of coffee.